Use the leading coefficient and degree of the polynomial to determine its end behavior. Then match the polynomial function with one of the graphs. First of all, I want you to remember that the end behavior of polynomials is determined by the leading term. And we've already studied two types of polynomials, the quadratic and linear. And it ends up that the higher degree polynomials have very similar end behavior. In particular, polynomials with even degree behave very much like a quadratic function in terms of their end behavior. If the leading coefficient is negative, the end behavior is similar to that of y equals minus 1x squared. If the leading coefficient is positive, very similar to y equals x squared. Similarly, if the polynomial has odd degree, the end behavior is very similar to y equals the opposite of x if the leading coefficient is negative, and similar to y equals x if the leading coefficient is positive. So in our first case here, t of x equals x to the fourth plus 4x cubed. Our leading coefficient is 1x to the fourth. The behavior is going to be similar to that of 1x squared. In other words, it goes up when x decreases without bound and up when x increases without bound. So let's look at our given functions based just on our given graphs based just on their end behavior. We'll exclude the first one because y is going down or getting smaller at the left and the right. The second graph is still a possibility. The third graph is going up to the left and right as well, so it is still included. The fourth, fifth, and sixth graphs are excluded because y is getting smaller either when x is increasing or decreasing. So we have two possibilities, and we will choose between them based on their zeros. So the original function, x to the fourth plus 4x cubed, can be factored as x cubed times x plus 4. There are only two zeros. That is x equals 0 and x equals negative 4. So we have to exclude the second graph because it does not have 0 at negative 4, and it has zeros that we are not interested in. When we go down to the third graph, we hope to find that its zeros are negative 4 and 0. And they are because the x-intercepts are negative 4, 0, and 0, 0. It also goes up when x increases or decreases without bound. So this is our graph of y equals x to the fourth plus 4x cubed. Now we'll look at a second example. This example is u of x equals the opposite of x cubed plus 3x squared. The leading coefficient is negative 1x cubed. And so the end behavior will be very similar to y equals negative 1x, which means that the graph should go up as x decreases and down as x increases without bound. So the first graph does have that behavior. The second does not. The third does not. So we're looking for end behavior similar to that of y equals the opposite of x. The fourth doesn't work. The fifth is a possibility. The sixth is not. And so we have two choices, the first or the fifth. Again, the zeros will help us choose between those two. So this time, let's factor out negative 1x squared to leave us with x minus 3. So the zeros are x equals 0 and x equals 3. We're going to throw out the first graph because it has too many intercepts, too many x-intercepts. So we'll go down to the fifth graph and confirm that its x-intercepts are 0, 0, and 3, 0. Notice that as x decreases without bound, the y is increasing. As x increases without bound, y is decreasing. So we choose this as the graph of y equals the opposite of x cubed plus 3x squared.